Good afternoon, everyone. Welcome to the Samvaad Talk series. Today's final talk on the theme 5G verticals and rollout is by Dr. Priyanka Das, who is going to speak on an overview of key technologies in physical layer security. Today's session chair is Professor Nikhil Krishnan M, who is currently working as an assistant professor at IIIT Bangalore. Professor Nikhil received his BTech degree from Amrita School of Engineering, Amritapuri campus, Kerala, followed by his ME and PhD from Indian Institute of Science, IIIT Bangalore. Prior to joining IIIT Bangalore, he was a postdoctoral fellow at the Department of Electrical and Computer Engineering at University of Toronto. His research is primarily focused on applications of coding and information theoretic tools to solve problems in distributed storage, distributed computation, and low latency communications. So over to you, Professor Nikhil.
Yeah, thank you, Amrita. So let me introduce today's speaker, Dr. Priyanka Das. Dr. Priyanka received her PhD in Electrical Communication Engineering from IIIT Bangalore in 2018. She obtained her MTech degree in Digital Signal Processing from IIT Guwahati in 2011, and the BTech degree in Radio Physics and Electronics from the University of Calcutta in 2009. She worked in Nokia Solutions Networks Bangalore as a summer intern in 2015. She worked in Dell Research and Development Bangalore as a software associate engineer from 2011 to 2012. Presently, she is an assistant professor at IIIT Bangalore. Her primary research interest broadly lies at the intersection of probability theory, optimization, and wireless communication, where she seeks to develop new analytical tools for understanding and enhancing the spectral and energy efficiency of next-generation wireless communication systems. Her current research interests also include cognitive radio, MIMO, physical layer security, intelligent reflecting surfaces, and machine learning for communication. In today's talk, she will be giving an overview of the key technologies in physical layer security. So over to you, Professor Priyanka.
Thank you, Professor Amrita and Professor Nikhil. This is the last talk of our 5G verticals and rollout series. I would like to thank the Samvaad team to give the opportunity for giving this talk on physical layer security. So this work started with the first, my first research student, Pradumna Hegde. He joined in IIIT 2019. So without further delay, let's go to the outline of the today's talk. So first, since the talk is on security, so we have to first see what are the typical security approaches in today wireless network scenario, and is there any challenges associated with it. Then why physical layer security will play a vital role in future. So we have to see what is the background of physical layer security, followed by we will see some of the key physical layer security techniques that will be used in go ahead future wireless area network. Then we focus on what we are doing as part of the PLS research in our group, and then I will summarize. So coming to the introductions of why physical layer security is at all needed. First, let's see the scenario of Internet of Things. So here you can see the picture that there are a lot of smart enabled different applications. For example, smart traffic system, smart home, smart healthcare, smart building. Okay, everywhere we are incorporating a word called smart, but you have to understand what is the basic things behind making this system as IoT enabled wireless communications. So these are the sensing devices, and this will capture the data, and we have to process the data to understand what's actually happening and control the environment or wherever these smart sensors are equipped with. So coming to the features of Internet of Things technology, this is a very promising area if you want to do research, and I hope some of you are already doing research in IoT and security. So there are a lot of different varieties of ways you can see that one can pitch in. For example, the intelligence or machine learning based thing can be embedded with IoT technology. There are a lot of devices, for example, billions of devices are connected through IoT, and you should be worried about the connectivity. Are all these IoT devices are connected to the internet or not? And with the advancement of new technologies, we have to deal with susceptibility and more devices to be connected. Sensing is another way where the captured data has to be sensed. Experiencing, you can also talk and they will act according to your instructions. There are two vital things that I want to highlight. One is the energy, where your energy will come from the power hungry applications of Internet of Things. We can not allow them to drain your battery as fast as possible. So you have to recharge them too often in that scenario. So we have to design energy efficient protocols for this IoT devices. And the topmost thing is the safety of this IoT enabled devices. Now, today I am focusing on the last part, that is the safety feature of the Internet of Things technology. Coming to safety or security in wireless, because all we are talking about a wireless media. So what do you mean by a security, and why the security is going to compromise in a network which is not wired, but it's a wireless communication? So when we talk about wireless communication, the first thing that will come into our mind, it's a broadcast nature. The broadcast media will allow your transmission not to traverse in a proper directions, but to diverse in various directions, and anybody in the air can overhear your information. So your information is vulnerable to eavesdropping attack. Someone is going to overhear your message, or they can also alter or modify the message content, which is a critical security threat. Why security is important? We all know that IoT data may contain sensitive or private or confidential informations. For example, when we talk about sensor node, it collects the patient's healthcare information. You can talk about defense or finance sectors where security is the topmost priority. And IoT systems are far from the safe and prone to different type of hacking or attacks. Okay, so that is the motivations we want to answer in today's talk. Are we doing the correct way of securing the technology? So the security today relies on the cryptographic techniques. Okay, so before moving or jumping towards PLS, physical layer security, we always have to see our friend, which is cryptographic techniques. Now coming to the security by cryptography, which is the conventional way of securing the network, right? So here, when we talk about cryptography, first thing we have encryption and decryption. So encryption is nothing but it's transform your plain text into an unreadable ciphertext. Okay, so unreadable ciphertext is the text that you are going to send over the media so that nobody can exactly get the informations if he or she doesn't have the keys, right? So it's a key-based encryption algorithm. Now at the receiver end, the opposite one has to perform, which is the decryption, which is you have to convert from the unreadable ciphertext back to your readable plain text to extract your message. How you do that? Basically, the key-based cryptographic techniques. And when we read some papers or we take a course on network security, you will learn a lot of key-based secret key cryptography or public key cryptography techniques. So I'm just giving the outline of this. We are not going to see too much in depth of the cryptographic way of security. So secret key cryptography, where basically we take same private key both at the encryption algorithm and while doing decryption at the receiver. So you have a plain text, with the help of the secret key, which is being shared to both the legitimate receiver and the transmitter, you are going to do encryptions, convert into ciphertext, and then the receiver will do decryptions and then get back to your plain text. Another way is called public key cryptography, where instead of secret key using both at transmitter and receiver, we use a public key at the transmitter, whereas we use a secret key at the receiver. Both keys are different, and these all involve key distribution and management to legitimate receiver appropriately. The third category is the hash function based. Now, what's a hash function algorithm? There are different varieties of algorithm are there. Basic idea is very simple. You have a plain text. You are going to convert to a ciphertext without the help of any key, but using some algorithm called hash function. And the hash function is one-way crypto, because once you get to the ciphertext, you cannot get back the plain text from the ciphertext. So the security will be more strengthened compared to this secret key and public key cryptography. But all these mechanisms will suffer from some disadvantage. We will see soon see what is this. Okay, so this is coming to the limitations of cryptography. Okay, so as I am mentioning that when we talk about a scenario called IoT, where we have a massive number of devices and they have to be connected to the internet, and they are energy hungry applications, and they are also size constrained. So executing the complex encryption decryption algorithms at the transmitter and receiver end might be not energy efficient. Okay, so it requires extra resources for all these computations, maybe not suitable for all varieties of applications. The second point is that it requires a delay for computations. So when we talk about ultra reliable low latency communications, it gives a full stop here. So we need to rely on not so high level computational intensive cryptographic approach, but is there any other way of securing the message? Okay, and further, when we talk about supercomputer or quantum computing, this encryptions and decryption keys can be broken. So it has unbounded computing capabilities, and it has the ability to guess the secret keys. Quantum computing is another future aspect that that leads to some another paradigm of the cryptography. Okay, or we called some another way of achieving the security techniques. Okay, so now when we talk about the communication stack, okay, so we have application layer cryptography, then we have transport, network, link, and physical layer. So we are talking about no, I don't want to rely only on the application layer cryptographic techniques, but can I do something basics on the physical layer itself, which is does it make sense? So we are talking about focusing only on the physical layers part to secure our systems. So let's see what is the key differences of cryptography versus physical layer security. Okay, so now coming to the physical layer security differences. So first to set up the model, first let's see what's happening in crypto. In crypto, when we talk about receiver, we get signals from the channel, And we have a physical layer. Physical layer basically responsible for demodulation and decoding. We will get the bits, the reconstructed bits or estimated bits, which being transmitted by the transmitter. Then basically our application layer security algorithms will be implemented with the help of the keys, and finally you will get a secure message. Okay. Now, in contrast, when we focus on physical layer security, as the name suggests, physical layer, your every this dash line dash this block is shifted completely in the physical layer itself. So what will happen? You have a transmitter, you have a channel, and you have a receiver. Now all the sophisticated signal processing coding algorithms you implement in the physical layer itself, such that you will get secure bits right at the output of file layer, and hence you do not have to do so now I am talking about you don't have to do anything on application layer. That's why the scheme is called physical layer security. Now in future it will be very appropriate and give strong reliability and security when we merge these two, called both the cross layer way of coming the security point of view. You can merge the application layer and physical layer, both the ways we can secure the message depending on the varieties of applications that we are talking about. So since cryptography algorithm is well established, but what we are not so sure about how the physical layer security will help us, or even what is the basic means, how can you secure in the physical layer. Okay, so if I want to compare, so we see that if I only focus on physical layer, there are no key involved. So the process that we are talking about, key distribution and management, which is a complex task here, will not play a role here. It is independent of the key. And also when we only focus on cryptography, due to the supercomputers and all, if the secret keys are the keys are compromised, your security is compromised. So then we are no longer in the safe zone. So with this introduction, let's jump into what's actually physical layer security. Okay, to understand this, we have to change our path from the basic communication to information theory. So the source of physical layer security is exactly comes by the Shannon's principle 1949. So he proposed what's the channel capacity is. The channel capacity is what's the called maximum rate at which the information can be transmitted over a communication channel with arbitrarily low probability of error. So if you are transmitting the rate at capacity, you are making sure your probability of error is low. But if you are transmitting at a rate which is higher than channel capacity, you cannot guarantee a low probability of error at the receiver. Your signal will be error prone. Okay, so the channel capacity is the limit of the transmission rate at which a reliable communication is possible, and which is actually proved by our father of communications, Claude Shannon, in 1949. Coming to it's more into this. So let's talk about a AWGN channel, which is very familiar with all of you, I hope. And this under AWGN channel, we know that capacity has this important notations: bandwidth times logarithm base 2 1 plus SNR. Okay, so the SNR is your signal to noise ratio, and you can write a very simple expression, the signal power divided by the AWGN, that noise power sigma square. Okay, if the noise is modeled at additive white Gaussian noise. Okay, now this is the so we understand what the capacity is all about. Now we need little bit more into the info theory. So there, as the name suggests, why it is called information theory. So let me give you the definitions of what's the information content. Okay, so the information content is given by h of xi, which is logarithm of 1 by P of Xi. So what does it indicate? So let's say your probability of a message outcome is very high. That meaning that information content is very less. But if the probability is very less, which means that it is less likely to occur, then accordingly the associated information content will be higher. So it captures the notion of uncertainty associated with the message, and it is given by mathematically log of 1 upon the probability of the occurrence of the message xi, where ith message is xi. Now we talk about the average information content. Okay, so this message maybe it can be generated from a random variable. So when we talk about average, we will do average over the PMF, which is P of Xi, and this is my average information content, which has a special name called entropy. Okay, now coming to the another definition, which is mutual information. So mutual information between the two entities X and Y is defined by this. Okay, so here you can see that this is the amount of information X conveys about Y. Okay, so X and Y, you can think about there are two, one is transmitter end or one is receiver end, and there what is the mutual informations that X conveys about Y is given by this formula. Now to give more understanding about this, let me just give a quick example. Take an example of noiseless channel. So for example, we talk about a noiseless, right? So there is a input which is x1, x2, xm, and the output is y1, y2, ym. And we have the probability, transition probability is showing the value 1 here. So because what is the input, that is going to see the output exactly same as it is. X1, the y1 will be x1, y2 will be x2. So you can write the noiseless channel by this transition probability matrix, that P of yj conditioned on xi will be 1 if I is equal to j. Okay, and it is 0 if I not equal to j. Okay, so given xi, the probability of yj given xi is equal to 1 here. Now with this basic definition of noiseless channel, our aim is to find or understand what's the mutual information between x and y, where x is 1 to m and yi is 1 to m. So joint probability mass function is very simple. So you can just use your basic formulas, just split it off into the conditional one and the P of xi, the priority probabilities. And since I equal to j, this is 1, so you will get P of xi only. Else you will get 0. Okay, now if you want to compute the mutual informations, which is in the form of h of y minus h of y given x, then what exactly you will see is the formula very interestingly coming to 0 because of the special form of this. Okay, not always it will come 0, but this is an ideal case where we can see that h of y given x. How do you understand given x? The uncertainty about h of y, the uncertainty about y, which is given by h of y given x, which proves to be 0. Okay, so that meaning the informations at the output is exactly the same at whatever the informations you transmitted at the input. So you will get I of x comma y is h of x, and also you can also say prove that this is equal to h of y. Okay, so this gives that idea. Okay, whatever I am transmitting, that is not lost during the transmission of through a noiseless channel. This is the ideal channel. Okay, now come back to our scenario. We'll talk about a security attack. So there, what we have is basically 3 nodes. Okay, so this is very familiar notations: Alice, Bob, and Eve. Alice is the transmitter. Bob is the legitimate receiver. That's called main channel. Main channel is the channel between the transmitter and the actual receiver. And there is a wiretap channel, which is nothing but the transmitter and the eavesdropper. Okay, this is the eavesdropper that wants to overhear the actual information. Okay, now Why I showed all these information theory, entropy related notations? Because right from here, we are going to see the mutual informations that, or you can see the what's the amount of information Bob is going to receive from Alice. That is nothing but captured by the mutual information between Alice and Bob, which is given by this formula. Similarly, you also know the mutual information between Alice and Eve, because Eve is also trying to overhear your message. This is h of a minus h of a given E, right? So now our goal will be to maximize the information received at Bob, at the same time minimizing the information received at Eve. Okay, or in the literature of physical layer security, there is a term where they are talking about the difference term between the IAB and IAE. Okay, so this is the net objective functions that we are going to maximize over the PMF of the Alice. Okay, so this is a very crucial metric in our case, and this sometimes called secrecy rate. Okay, secrecy rate is nothing but we will see that it is the rate of transmission that can reliably be supported by Bob and not be able to decode by Eve. Like the Shannon has showed the capacity, which is the maximum rate at which the information can be transmitted with low probability of error. In the notion of secrecy, we will call this is the maximum rate at which the information can be sent to Bob, while we make sure that eavesdropper is not be able to decode, or the perfect secrecy is maintained. Okay, now this term, you please notice, this is called secrecy rate, and it plays a crucial role in physical layer security. So to understand this why part, let's see two wiretap channel model. I will see the main two. One is Shannon and another is the Wynard wiretap channel model. So what Shannon actually proposed is you have a Alice and you have a Bob. The transmitted information is X of n, and the Bob is the legitimate receiver, which is receiving B of n, and there is a Eve which is receiving E of n. It is a yn because it is a nth ordered extended message. Okay, or you can say a block of message, a number of x1 to xn. And there is a secret key. The Shannon showed the key involvement right here. Secret key being shared by Alice and Bob, but Eve doesn't have the secret key. Now, this information theoretically secure communication is achieved by using the same random secret key. So, which was shown by Shannon in long back. Okay. Now, perfect secrecy is achieved in information theoretic notion when we call the information to eavesdropper from Alice is 0, or mutual information is 0. Or in other words, the second term of mutual information, h of a minus h of a conditioned on en, has to be equal to h of a. When the second term, or the uncertainty upon receiving the eavesdropper, the uncertainty about the original message is the complete message itself. There, if you just subtract h of a minus h of a given en, you will get the term which is 0 for the mutual information. Okay, and Shannon also proved that this is possible, not for always, but for a special case where the secret key k, the entropy of h of k, if k models the random variable associated with the key, then the entropy of this random variable k should be greater than h of the the actual message a. Okay, so this is nothing but the key length should be longer than the actual message length, confidential message length. So under this situation, he showed that perfect secrecy is possible to achieve. Okay. Now, again, this is a key-based mechanism, and it has its own disadvantage that we are talking that we don't want to be rely on key-based secrecy algorithms. So now the question is how. And after 25 years, Weiner came up with the famous wiretap channel model, where you have a source, you have an encoder, you have basically two channels. One is main channel, another is the wiretap channel. The actual information is here: source, encoder, main channel, and decoder. And after the decoder, it will decode the estimated message of AK. SK cap is nothing but the estimated message of AK. And there is a eavesdropper channel or wiretap channel, which will decode it, and it will get the information En. Now, why K and N? Because it's a encoding scheme. You have a block of K bits which are going to encode to a block of N bits. Okay. Now, this is a very classic paper in PLS and cited. You can see the citation number. So they are basically the key. There are two parameters in the whole paper. If you just read, it's very nice paper. There are two parameters. They are talking about transmission rate K by N, which is we all know from our information theory background. And there is a special term called equivocation rate, which is a measure of confusion at the eavesdropper, which is nothing but the conditional entropy, that is received En. What's the uncertainty of A? That is the actual source message AK. Okay. And since it is a block of K source bit, we are dividing by K to get a term which is nothing but capturing the measure of confusion at the eavesdropper. Okay, so if this term is equal to your H of AK, then you will say measure of confusion is the fullest, or the eavesdropper is confused fully. That is the ideal situations we all want to achieve. Okay, so now let me see if I want to give a plot between the transmission rate, which is in the x-axis, and the equivocation rate or the measure of confusion by the eavesdropper along the y-axis. You will get a very interesting result, which is proved by Weiner's paper. So you will get this. So now there are a couple of things you can see, that if I am increasing R from 0 here to value, then my confusion or measure of confusion is the fullest, which is the entropy of the actual message H of S. Hence, the mutual information will be 0, because my D is basically captured by this formula, this delta formula. This is the measure of confusion. So this is the fullest confusion. But once the rate R just crosses the boundary CS, you can see how it is degrading. That meaning that the eavesdropper is now confused, is not confused fully, but the rate of confusion is less now. So that meaning your security is going to compromise in this situation in the right hand part of this line. Okay, and the CM is the capacity of the main channel, the Shannon capacity log of 1 plus 2 SNR of the main channel. Now, what is this CS? The CS, as we talked about, this has a special term, and just I have shown the CS is nothing but this term, which is the difference between the capacity of the Alice to Bob channel minus the capacity, which is max I, Alice to Eve channel. So when we compute the capacity of main and wiretap, I will give the difference between this captured the term called secrecy capacity, and that secrecy capacity will exactly give you the term that we are looking for. That is, what is the rate at which if you transmit from the Alice end, you will not confuse the eavesdrop. You will get perfect secrecy. That meaning the confusion rate of confusion is the fullest, which is the H of the actual source message, the full entropy. Okay, but if you transmit at a rate crossing CS, you are getting degradation, and when R is exactly equal to CM, you will get this. But you cannot even transmit. Now the basic Shannon regime is here. When R is greater than CM, you know that your reliability is even lost, because this is more than the capacity of the main channel. Okay, so here we are. So the point of interest for PLS is this particular shaded region. When we talk about I cannot transmit beyond this rate which is captured by CS, and this CS amount is nothing but CM, the capacity of the main channel, minus the capacity of the eavesdropper channel. Okay, so that is the punchline of entire talk. Perfect secrecy is achieved when limit n tends to infinity. So since we are doing an encoding scheme, this perfect secrecy is achieved when we have these situations, and we have just concluded that if R greater than secrecy rate CS, outage event, secrecy outage event occurs. When R less than CS, we have perfect secrecy, complete equivocation of if. Okay, now to give what's the called secrecy capacity, this is the highest rate at which complete confusion for eavesdropper happens. Or if you just cross CS, you are going to compromise with the security. Okay, so the same thing in a different manner. Now, what do you mean by positive secrecy versus no secrecy in information theoretic sense? So now we will see these two pictures. Let's say the Bob is very close to Alice and eavesdropper is quite far away. Now, what you expect is the capacity of the Bob channel is better. Okay, and you will get a positive secrecy, meaning your secrecy rate is greater than 0. Or CB is greater than CE. The main channel capacity is greater than C of E, and you will have a positive secrecy, meaning your communication is safe here. But when the eavesdropper channel is better, for example, the eavesdropper is very close to the transmitter than from the actual receiver, then the eaves channel is better. The secrecy is 0. CS is 0. Okay. So this is the thinking punchline that you have to think how to make eavesdropper channel more noisy. Okay, I want to make the eavesdropper channel more noisy, but without relying on secret or private keys. Okay, so with this, let me start with the key PLS techniques. There are multiple techniques people are looking from, right from a MIMO, antenna selection, beamforming, artificial noise, cooperative relaying and cooperative jamming, and also the new IRS. So all are going to help in some sense to improve the physical layer security technique. That is how you can make the eavesdropper channel more noisy compared to the actual channel. Okay, so with this, I will dip into some 4 topics here, small, but we will just keep the overview, not will go into much of depth. So what's a MIMO beamforming? The MIMO beamforming, all of us know, but it is used to make a directed beam towards the legitimate receiver, which is Bob, but it will give a complete or a null, it will set a null towards the eavesdropper. It suppresses the reception in the direction of the unintended user. Okay, this is energy efficient scheme because the energy is completely focused in this main lobe. The side lobe, we have a if, and we want to suppress the transmission from Alice to Eve. But there are multiple optimization problems here. Our research goal may be designing the optimal beamforming matrix to maximize the performance metric, which is secrecy rate in our case. Second is artificial noise. So what does it mean? So you don't have a MIMO setup here. It's a SISO system. You have a single antenna, but the Alice is going to transmit another signal, which is something like an interference signal, where this is called AN, the artificial noise signal, some interference signal, such that you can see there is a eavesdropper and this is the actual signal. So I want this to be secure, but this to be suppressed. So this artificial noise has to be designed in such a way that it is going to interfere to a severe extent to the eavesdropper, but it will not going to show any impact towards the Bob. Okay, so the idea is cancel its effect at Bob and degrade the signal received by Eve. Okay, how do you do that? Coming back to linear algebra, so basically we have to see that the AN, the artificial noise, has to be designed such that it lies in the null space of the Bob's channel, and in the range space of the eavesdropper channel. Okay, so there is a design policy associated with it. Okay, so this is some techniques. Now coming to the third, cooperative relay selection. So this is no, I have given multiple talks on that. So this is source and destination and relays. Now relays are going to help not only providing reliability, but they can also help in boosting the secrecy performance. Okay, and they are helpful when we talk about single antenna system, which can be your sensor node or handheld terminal due to size and complexity constraint and power constraint. So you go for cooperative relaying, and it can help in improving the secrecy capacity. How actually? So the term is called cooperative relay selection. So basically we are going to form the secrecy rate, and the secrecy rate will be different via different relay links. Now you pick up that relay that maximizes the secrecy rate, as simple as that. But the main challenge is the analysis. How do you, with that best selected relay, how you are going to show different performance metrics, that is the secrecy rate or secrecy outage probability in that particular setup. Okay, so this is another umbrella that research goal: find the optimal relay to select, maximize secrecy, to maximize the secrecy capacity. And again, the problem can be different when you talk about a amplify and forward protocol or a decode and forward protocol. Okay, so this is another direction. Now the fourth one is the cooperative jamming. So this notion is very similar to your artificial noise, but it's not achieved by the MIMO. Otherwise, it is achieved by a cooperative relay, which is called a special name cooperative jammer. It tries to jam the signal towards Eve. So you can see that Bob is getting two signals from Alice to Bob and a jammer to Bob. So it has two channels here. And similarly, eavesdropper will get two signals. One is direct from the transmitter, one is from the relay. Now, what is my intention is, again, I will design the cooperative jamming signal such that my secrecy rate will be maximized. So in this case, you can write your equations, or I just give you some kind of hint that you will get two signal. One is from Alice to Bob, another is from jammer to Bob, and there is a weight factor associated with it. They are doing some kind of weighted average jamming signal. And final goal is to maximize the secrecy rate at the Bob, because Bob is the legitimate receiver. And by how you are going to optimize the relay weights W. Okay, so this is another optimization problem. So this is the difference between the main channel rate and the capacity of the eavesdropper channel. You can see this. So when we come the main channel, the signal power is this actual signal power, and the noise power and interference power is this. So that's how the rate formula is given here. And you want to maximize R subject to W. Okay, you have some constraint on the power also from the cooperative jammer. So this is another directions. Okay, now I will give the limitations and I will come to what we actually did here. The limitations are when we talk about your MIMO beamforming or the artificial noise aided security. The first of all, you have to solve different optimization problems, come up with your optimal beamforming weights, which might be non-trivial to come up with in different scenarios. Okay. Second is there will be very difficult to ensure that absolutely zero leakage to eavesdropper, and you will get main beam focused into the Bob. So leakage is another issue. And when we talk about the artificial noise precoding, their signal has to be sent to artificial noise has to be sent to both the actual receiver and this. So it needs an extra energy spent in generating this artificial noise, which might be energy inefficient technique. And also the crucial point is all these techniques that we talked about, when we will see what is the optimal beamforming weights and all of them will in turn rely on channel state information's availability of the various channels. It will also be Alice to Eve and jammer to Eve. Now you notice that the channel state information of a eavesdropper, getting the eavesdropper channel perfectly, quite instantaneous channel is very difficult, because I don't know exactly where the eavesdropper is. It might be difficult to acquire this CSI of the eavesdropper channel, and that's why the challenges of implementing all these schemes will come up. Now, but we have to rely some kind of no information. We have to rely on, or we have to come up with a CSI acquiring mechanism to perfectly apply this algorithms for physical layer security techniques. Okay. Now, with this, I'm coming to the last part. So what we did in our research is we take help of two technologies. Okay, so one is your, as I mentioned, that these cooperative relays are very helpful in a situations when you don't have multiple antennas. They can be act like a virtual antenna array, and they can be selected, or all of them can be transmitted. Here we talk about selection, so I just focused on the selected relay transmit to forward or to help forwarding the data from source to destination. It has some other advantages. For example, when we talk about selection only, it doesn't have to maintain the synchronization among all the relays. And also the another big advantage is it only needs the channel amplitude informations. No channel phase information is required in this selection policy. Hence, it is complex, low complex than the other relaying strategies. This is the number one technology that we borrow. Second one is the antenna selections of MIMO. So here we basically marry the two technology. One is the relay, cooperative relay, and another is the MIMO. Now you have a MIMO, and basically you can do beamforming, you can do AN precoding, artificial noise precoding. But why not to just go the antenna selections? Because antenna selections is the scheme where the best antenna will be selected among all the other antennas. It is very less complex, and we need one RF chain instead of all the N RF chains, which is costly to switch to all the RF chains. And no, we have a background, we have all this VLSI amplifier, mixer, and all these techniques. Now, if you are relying on only one RF chain, your life is simpler. But yet, it can be proved that with choice of appropriate antenna, you can also exploit full diversity. That's the plus point of antenna selection. And as the relay selections, it also needs channel amplitude informations, because getting channel amplitude is easier by estimating the power compared to the getting the channel phase information. Marry both this. Okay, now you can do something better. And together we focus on a practical setup, which is the spectrum sharing network, where we talk about, I'm not going to give the introductions here, but it is basically the spectrum sharing concept is something like you have a spectrum resource, spectrum scarcity, and which is very obvious in IoT setup, because you have billions of connected device, you have to tolerate more connected device, and spectrum will be a crucial resource there. So why not to use some spectrum sharing policy, and you focus on underlay mode. Basically, what is the notion that both the primary and secondary are transmitting at the same time in the same band, but there is a catch that the interference the secondary causes to the primary is to be maintained within a certain tolerable threshold. Because I am going to use the spectrum of yours, you are the boss, I cannot cause too much of interference to you such that your communication is going to hamper. This is the constraint that you have to keep in our mind. And this interference constraint is the bottleneck of the secondary users communication to go down. Okay, so in this case, secondary user performance is going down, okay, for the spectrum sharing setup. But the plus point is you can employ some sophisticated techniques to improve the performance of the secondary system. and also improve the security, because we are talking about security and we focus on security basically for a spectrum sharing network, which might be more relevant when we talk about multiple devices is coexisting. Multiple devices are coexisting in the same spectrum, because spectrum is a precious resource. Okay, with this, coming to our model. Now, this is our system model. We talk about spectrum sharing primary network. This is the transmitter, this is the receiver, and there is a secondary network. Now, as I mentioned, we are going to use two technologies. One is MIMO, another is relays. Where is MIMO? This is your source. Secondary source, multiple antennas, secondary destination, multiple antennas, and there is a eavesdropper which also equipped with multiple antennas, and there are some relays, cooperating relays. We assume they are single antenna enabled, because they might be restricted to have single antenna in some sensor based relay networks, which is low power constraint. Okay, now in our setup, we want to see different things. First is the power control. Okay, because it is a spectrum sharing network, the major you have to keep in your mind, I cannot cause too much interference, and I have to meet the interference constraint like this. Okay, this is a maximum power constraint and this is the maximum interference constraint. Okay, so the power is limited. Okay, now what we did with your multiple antennas is you do a transmit antenna selection at the S source and the receive antenna selection at the destination, and also eavesdropper does antenna selection. Okay, we assume for simplicity of our analysis, frankly, there is no direct link from source to destination. This may also be practical if this is a deep fading or shadowing between the source, or it's a high path loss. And also we assume there is no direct link from S to E, but the reviewer will shout if you do not show a line. But to start with, for simplicity of analytical expressions, we do not assume a direct link. Okay. Just bear with this small point here, but let's see what's our objective function. In practice, it will be good if you can extend a direct link from S to E and S to T. That will be the optimal way. But just to go ahead, we assume no direct link due to heavy path loss or shadowing. Okay, now what is our target? We want to maximize secrecy rate, because this is the performance metric that I am talking from the very beginning. The secrecy rate is defined by the difference between the main channel and the wiretap channel. And since it's a rate, it cannot go less than 0. So we have a take max of 0, this. Now from our model, we then write the equations this. Okay, so this is our main channel half log of 1 plus SNR. This is the SNR of main channel, and this is the SNR of eavesdropper channel. After doing antenna selection, we have a maximum SNR based antenna selection at the eavesdropper, because eavesdropper can do the best antenna to select, can select the best antenna to hear the message for its own benefit. Okay, so this is my secrecy rate. Now, what's your problem? Now, we are going to answer the physical layer security by selecting the best antenna at source, the best antenna at D, okay, and the best relay. There are L number of relays, which is the best relay, such that the source will transmit the message via that relay to the destination. Even if the relay overhears the message from the relay, the eavesdropper overhears the message. This is my eavesdropper link. The blue line is the wiretap link. The green line is the main link. And since this is an interference aware situation, spectrum sharing, you will have this dotted interference link. You have a source interfering to X, which is primary receiver, and you have this red line interference link to X, and also you will get some interference from the primary transmitter. Okay, this is this line. Okay, so with all these channels putting all together into the small expressions, we'll get this expression. Okay, now once you formulate your problem and once you identify what is the secrecy rate in the function of I, J, K term, now a very high school mathematics you can apply. What is the best option to select I, J, K is nothing but you maximize this term, and logarithm is a monotonically increasing function. So you pick up ijk, which maximizes the inside term. That's your policy. Okay. So before this, I want to go into the practice theory from we are now in theory. Let's see the practice. And in practice, what type of cyber security risk we'll have. Okay. So we have basically two attacks. One is the passive attacks, one is the active attack. Okay. Now in the passive attack, basically what is happening is this. Now attacker intercepts information without changing it. There is a hacker. It uses the information, it's going to overhear your information, but it doesn't want to change it. For example, the cases like gathering human and machine identities, their locations, they just want to gather information rather than tampering with another content. Okay, so this is called passive attack. This is very hard to detect because we do not know the information is being modified. Secondly, there is an active attack where the attacker intentionally modifies your information content, and the use case maybe it can know it's a very serious issue. An intruder will pretend to be another user to gain access. Okay, it steals packet, it's more likely to detect. So we have to keep in our mind there may be a passive eavesdropping versus active eavesdropping, and we have to answer both these cases. What will be your optimal selection policy, relay and antenna? What will be your optimal selection policy for both the cases? Okay, so we focus both active and passive eavesdropping. Now go back to theory. So in first case, when we do active eavesdropping, meaning you active meaning the attacker the eavesdropper information is easy to achieve. Where is the active eavesdropping meaning is like your eavesdropper may be also acting as a legitimate receiver, but it wants to change your information. And in that case, we can see that the selection policy is the one which maximizes this inside term. So here you select the relay index I star, transmit antenna index J star, and receive antenna index K star, such that this term is going to maximize. You are going to maximize the inside term. Okay. So now, obviously it will be performing the best, because once you know the eavesdropper channel information also, you can basically pick up these parameters such that your secrecy rate is maximized. So this is the optimal way to do it. But catch is, yes, you need to know the SINR of relay to eavesdropper channel perfectly. Okay, so this is the catch. We have to know it. But assuming this is done by somehow, then this will give you the best performance or theoretical upper bound for the secrecy rate. Okay. Now with this I will show few results, 2-3 results I can show. So in this case, we consider one case when we plotted secrecy outage probability. Outage probability is nothing but what is the probability that your secrecy rate, there is an outage, right? So secrecy rate will be less than R, or so if you remember your plot, the R and your CS. So we have this and this and this. Now this is the point CS. So when R is greater than CS, I am calling secrecy outage event occurs. So this captures in the metric secrecy outage probability when the probability R is greater than CS or CS less than R. And what is your CS? That is the secrecy capacity. Fine. So we have considered two scenarios where main channel SNR is also increasing and eavesdropper channel SNR is also increasing. Okay, eavesdropper channel SNR also higher and this also higher. Under this, so this is fixed. This is fixed, not higher. The eavesdropper channel SNR is fixed to 10.1 dB. In this case, I can see that my main channel is very strong, but eavesdropper channel is somehow blocked. So which is a very the situations that might arise when there is a blockage between the actual transmitter and eavesdropper or some shadowing. Okay, so in this case we can see that your probability, the secrecy outage probability, is perfectly monotonically decreasing. It decreases. So as you increase your SNR of the main channel, it decreases. Okay, and what you can also see that when you increase the number of antennas or the number of relays, you get a benefit. Okay, so this gives you some intuition. Okay, so if you increase number of antennas or odd number of relay, you can actually give a better secrecy outage probability. That is, your outage probability is going down by increasing either L or mean of NS and ND. And we also showed that the diversity order, which captures the rate at which it is decaying at high SNR, this asymptotic curves, this is governed by this term, which is prominent from this formula. This is secrecy outage probability. It has two terms. The first term gives you the coding gain and the diversity gain. Okay, so this and this is controlled by these three parameters only. One is the number of relays, number of antennas at NS, which is the source end, the number of antennas at the destination end. When the SNR of the main channel is going to increase and the SNR of the eavesdropper is fixed. Okay, now you might raise your hand. What is happening when eavesdropper channel is also increasing? That is, eavesdropper is also close to the main transmitter. So in this case, we also have one plot like this. So when gamma is also going to high. So in this case, you can see that it is not monotonically decreasing, but secrecy outage probability is decreasing and then it saturates at high SNR. All right. So now we do not get that diversity benefit by using either N or L, but you will get a coding gain. You can see there is a decrement. If you increase, keep L equal to 2 and increase N3 to N4, number of antenna you just increase by 1, you get a shift. You get a decrement in the secrecy outage probability. But the this is no practical situations that when both the main link and eavesdropper link are of good quality, then as SINR increases, it decreases fast and going to saturate. So it will be saturating at this particular dash line, which is also proved by the asymptotic plot. Okay, so we have plotted all three: simulation, analysis, and asymptotic. They are on top of each other. Okay, now with this, and also we have proof that this is the expressions. We are not getting diversity order, but we are getting no benefit by increasing this, but we are not getting diversity benefit as opposed to the earlier case. Okay, now as I promised, we will be covering both active attack and passive attack. Now the passive attack is where the eavesdropper is it doesn't show you where I am. It's very difficult to predict where is the eavesdropper. It just try to intercept your informations without modifying it. Okay, so under this passive attack, where it is very hard to detect the presence of the attacker, and hence it is very hard to find the wiretap channel state information. In this case, you cannot run this secrecy rate optimal scheme because you don't know gamma RIEL. How do you know gamma RIEL if you don't know where is my eavesdropper is? And in this case, the best I can do is maximizing only the main channel capacity. Okay, so the optimal relay and antenna selection is completely focused to maximize the main link SNR. Okay, and this is the way, if I don't have any information about the eavesdropper, I am just going to stupid rule. Yet we will see how the performance is going to differ from the last one. But this is the stupid rule. Just focus on the main channel signal to noise ratio and select the option which maximizes this, which is mean of this. Mean because this is a DF relaying protocol and the SNR is mean of SR link and RD link channel. Okay, now let me come to the performance comparison schemes, because I have showed two schemes. One is this black curve. Okay, here you can see two type of curve. This is the curve that I talked, the perfect policy when you have the wiretap channel state informations available with you, you can do the best. Okay, and this dash dot line is when the eavesdropper does maximal ratio combining, because it is powerful. Let's say I am also consider another situations when a powerful eavesdropper can do MRC instead of selecting the best antenna. When it do MRC, its SINR is going to increase and the secrecy outage probability is going to increase, because it is now odds condition. The SINR of the eavesdropper is higher, which will decrease the secrecy rate or which will increase the outage probability. Now we talk about the other situations, passive attack, which is the red color plot here. The red plot is telling much above the secrecy outage probability is way much high. You can see the difference I have just marked. This is 10x versus this is 100x. So if you consider this 20 dB of SINR, you can get a 100x benefit when you come to the secrecy rate optimal scheme, which comes under active eavesdropping versus the passive eavesdropping here. Okay, and there is always a compromise between the two, and this blue one is the compromise one where we have statistical knowledge of the eavesdropper. This also a very interesting situations. Even if you don't have the actual information, somehow you can gather the statistics, which may change in a relatively low scale. You can be in between the two, and you can see the performance is quite close to the benchmark, the fundamental benchmark, which is the black one. Okay, so with this, the conventional relay and antenna selection performs the worst. Statistical relay to eavesdropper link CSI is helpful when full CSI is not available. And we also have compared the two situations when there is a eavesdropper does MRC versus eavesdropper does antenna selection. And MRC gives you worst performance compared to selection combined. Okay, so now I am summarize our talk. That the motivations was to give the idea of physical layer security techniques with its background. And in our research, we focused on a spectrum sharing network, and we considered a secrecy rate optimal relay antenna selection scheme. We showed it serves as a fundamental benchmark, but the catch is you have to know the relay to eavesdropper link CSI, which might be feasible for certain eavesdropping attacks, but not for always. Then we also proposed a suboptimal relay antenna selection scheme, which may be feasible for passive attack situations. We see that full secrecy diversity gain is achieved when both the main channel and the wiretap channel, when the main channel is strong, but the wiretap channel is severely blocked. Then we get full secrecy diversity, and you will get this, the decreasing nature of secrecy outage probability. But when both the channel are strong, both the main and wiretap channel are strong, we'll get the flat curve in the high SNR regime. Your diversity gain is lost. And the future work is going to do some kind of cross-layer optimizations, which will be more robust in terms of designing a secure, reliable, and energy-efficient wireless network by looking into different layers altogether, both by application layer and physical layer together to come up with your solutions for physical security. And thank you. So with this, I conclude my talk, and now I request, please ask any doubts, questions.
Hello, madam. I'm Shashikant here. Can I speak?
Yes, please.
Yeah. So thank you. It is very interesting lecture, different perspective. But my question is that is it this type of system is it practically realizable in the 5G?
Yeah, so coming to the practical realizable part, so that's why I have given two aspects. One is the kind of active eavesdropping and one is the kind of passive eavesdropping. So it depends on what kind of cyber security attacks we are target to build our algorithm on. So when we talk about cyber security attacks, it might be there are n number of attacks. So it's specific. So there is so the answer is yes, it is possible. Now it depends on applications, and it is not yet to the standard, but the research is going on to integrate the physical layer security along with the conventional crypto to build robust solutions. So even if the devices are not capable of running the computationally intensive algorithms, or it is no energy hungry applications, we can also rely. So it's another means of exploiting secrecy.
Yeah, thank you.
One question. How does this compare to the information, the security which you get? Of course, this is a okay. Here, simple. How does the strength compare to the information theoretic bound? I think it was derived by.
Yeah, so Professor, I think you missed the first part. So basically, I showed how from the information theory, this is basically information theoretic security. So this is the Shannon's formula that what is your capacity, and Shannon proved the first information, no, it's landmark result. So it comes from the information theoretic security.
Yeah, so I think later on there was the security by this guy at Bell Labs.
Weiner. So
Yeah,
Professor.
Weiner.
Yeah. So
are
if
you close to the his bound?
Weiner bound.
Okay.
Let me go back. I think I not understanding the bound part. One second. Yeah, so this is the Weiner's wiretap channel. And what he told is this. So the Weiner proved that if your rate of transmission is greater than a term called secrecy rate, then you are well in the good shape. You are going to confuse the eavesdropper by the fullest amount. And that's what we are targeting at. So every problem in the physical layer security, they first start, what is my secrecy rate? And they are going to transmit their rate such that if the rate is less than CS, they are good. But if R is greater than CS, the secrecy is compromised. So that's how the role of signal processing and coding and a lot of MIMO techniques to increase your secrecy rate as high as possible by doing different.
To what extent is semantic correlations incorporated? I don't think they've been done much in communication, but if I hear the first 2 lines of a story and I know what the story was about, the next 10 chapters are irrelevant. So to what extent is the semantic high level long range, where does the correlation structure analysis, what's the sort of correlation length which can be incorporated or has been incorporated in the paper so far? For example, I could, exactly as I said, 2 words I'll get, and then the rest is irrelevant. And I could be even below the threshold all the way, but if I can guess the first 2 words, I know the entire story. So the actual information content is very low because it's only figuring out which one of maybe 10 stories were actually being talked about. Simplest thing probably is figuring out which song it was. If you just know the tunes, even in little places, even spread apart, you can figure out what the entire song was.
Yeah.
So it's a question of length.
Yeah. So basically, no, this question is a very broad. So I am not getting the correct answer for it. But to give the idea where the physical layer security is can be shown to be secure enough, people are analyzing different performance metrics. For example, one performance metric may be the secrecy capacity. But secrecy capacity computations might be challenging if you do not have the wiretap CSI and all available. Then what people are telling, I cannot transmit with the rate of CS, but I know I change my R and I will see what is the fraction of time I am crossing the CS. And that
the thing is that only thing is the rate itself, let us say the entropy of information may appear to be in the short window high, but in a much, if you take an entire long transmission sequence, you can figure out the actual information is very low.
Yes.
So then the computation of information content itself starts becoming a little questionable, in that it depends on the length of sequence you get.
Yes.
Again, I am not being.
Yes, absolutely true. Absolutely true. So this is the Weiner's paper. They told if I make the length of the sequence as high as possible, I am in a good shape. But if you increase the length of the sequence n, the transmission rate is going to be very small here. So they are actually now, they proved in that paper that it is possible to come up with a non-zero rate such that the perfect security is still be obtained. The length of the sequence is, there is a question. I completely agree with you. Okay, any further question?
So yeah, Priyanka, a couple of questions from my side. So
Yes.
what was actually on that Shannon's pattern model, right? So because of that requirement h of k greater than or equal to h of a, right? I think it's like, I mean, so now the problem is like, I mean, how will you share the key securely, right? So it's as difficult as the original problem is. So in that sense, it may not be like, so there may not be much work on that direction, right?
Yeah. Yeah, so that's why Shannon told this, but it just a theory, and no one can go beyond that. And that's why this 1975 Weiner's paper really fundamentally changes the Shannon story, and it showed without relying on key itself, you can achieve approximately perfect secure communication.
So now the other question, so you have that quantity, right? The difference of musical information, which you are trying.
Yeah.
Right. But why are you saying that maximization happens at is precisely equal to the difference of the capacities? Because I mean the terms, we are basically trying to maximize the difference, but you are saying that
yes,
it is equal to the difference of the capacity.
Yes.
Trivial, right?
This part.
That's not trivial, right? So there is a derivation for that. I mean, so
yeah, it is. There is a. I missed that paper. There is a paper. They have proved that. So
okay. So
anyway, you can also
is,
do IAB by IAE. So why difference? The question is why difference, right?
Yes.
So
I mean,
this is
because maximization doesn't distribute over that thing, right?
So they told that it is the secrecy capacity is the difference between the two. Now the question is, and the Weiner's paper told that okay, secrecy capacity is the highest limit where you can achieve the perfect secrecy. But why the difference part, that I have to actually see this. But it is proved, already proved.
Fine. So and
I have to give the reference maybe here.
Yeah. So and one more question, like I mean, so it was on cooperative relay selections. I actually didn't get that intuition behind it. So in MIMO beamforming, we can like relate to it. Similarly, artificial noise, I can sort of see that, but cooperative relay.
This one, na? So basically, see, the cooperative relays are earlier. It is a 10 years old technique from the beginning. So basically, cooperative relays are made to transmit the informations to the destination. It's like a diversity scheme. One of the diversity scheme, if the direct link is bad, you can transmit via any of the relays. Why relay selection? Because selection helps mitigating a lot of other issues, synchronization issue and all this, and also need orthogonal slots to transmit one after another. Okay, now if you assume selection is the good way, next question is who is the best relay to select? Now the who part, the who is the best relay to select part, now it determines which is their performance metric to optimize for. Now the performance metric to optimize for was basically the SINR or the error probability in our 5 years back. Or even when I was doing my PhD, I looked at the problem. What was your error probability optimal or capacity optimal relay selection policy? There, we do not consider this additional eavesdropper. We just consider a simple cooperative relay setup without eavesdropper, and we come up with relay selection. Now, once your eavesdropper is there, now the situation is that you, even if you consider the error probability or normal capacity, this is not going to give you much benefit when we talk about security. So there people look into the performance metric change into the secrecy rate and secrecy outage probability, and also called sometimes called reliability or intercept probability. Intercept probability is what is the probability that your capacity of the eavesdropper is higher than the capacity of the main channel. So this kind of performance metric will be meaningful under the eavesdropper aided situations. And cooperative relays selection policy will be different depending on which will be your optimization metric. That's why the entire literature was relay and selection to maximize secrecy capacity or to minimize secrecy outage. This. And here we combined the two. Basically, the answer for only the relay is very trivial. The answer for antennas are also trivial. The non-trivial part is the analysis. And it is even difficult when we talk about a wiretaps spectrum sharing, where you have this power. If you do not consider spectrum sharing, your power is only Pmax. It has a fixed power. But when you have a spectrum sharing, you can see there is a channel sitting in the denominator, which is the interference channel. So this gives additional complexity in this, but it will give you extra flexibility to improve the performance by choosing number of antennas appropriately, choosing the which antenna to select and which relay to select. Okay, so this problem can be categorized into first maybe and first look at without relay only antenna. Second, you can look single antenna, single SISO system with relays, and then put MIMO system with multiple relays and do the joint relay and antenna selection. And we can prove that this is the optimal scheme because this is the my performance metric, and I just want to maximize the inside term. I'm done. But the practical question is how you are going to get the SINR of the relay to eavesdropper or source to eavesdropper. If I have a source to eavesdropper, I could have done a MRC technique here or add up or somewhere combining the both the signals. That also. So
in some sense, you are assuming that the eavesdropper is sort of cooperating in that sense.
Not cooperating, but so the literature says this is a very crucial question for this kind of paper, physical layer security, that how do you know this relay to eavesdropper channel? Yeah. So it only possible under the situation called active eavesdropping, where the eavesdropper is an active node. It's just like a normal destination, but it is unknowingly going to tamper your information. So, and how do you get estimation of this channel? Basically, this pilot based mechanism or feedback. Feedback. So if it is a legitimate receiver, somehow source could have estimated it and feedback and it got estimate. But somehow this legitimate receiver pretend as a eavesdropper, then it's called a active eavesdropping. But if it is a passive eavesdropper, then we assume that this is not available, and then this kind of scheme won't work.
That's what you were doing in the end, right?
Yeah, so that's why we have two papers. The first paper we struggled a lot in 2 times. The question is, how do you know this? Okay, to answer, we have to fight for a very hard fighting time to convince the reviewers, how do you know this? And then the easiest one is the passive eavesdropping, but always there is a compromise because you can see the performance gap is too high, and you can see almost it's a flat, but it is actually going is a good benefit here. So that's how our next work is to analyze the statistical relay and antenna selection scheme, where we are in between. You have some statistical knowledge, but it will help much from even you don't know.
Bridging the gaps.
But coming up with the analysis is another challenging task.
Thanks, Priyanka.
Okay. And this is the picture drawn by me and myself.
Oh, nice.
Okay, thank you. Any other question?
So yeah, if there are no other questions, so let's thank the speaker. Thank you, Priyanka, for the wonderful talk. And yeah, with this, we'll conclude the session. Let me hand over the stage to Amrita.
Thank you, Professor Nikhil. So I would like to thank the speaker of the day, Professor Priyanka Das, for a wonderful talk, and Professor Nikhil for coordinating and chairing the session. So with this, we would like to close formally our ongoing series on 5G verticals and rollout, and Samvaad is going to launch its next theme in association with the Cyber Physical Systems, or CPS SIG, with the help of Professor Sachit Rao on robotics. So more details will be shortly emailed to all the IIITB faculty and students. Thank you everyone once again, and looking forward to a participation next week. Thank you.